All right, good morning, everybody, and welcome back. How was your spring break? I figured it might be hard for you to enjoy spring break, knowing that test number 3 is looming around the corner, and also it's the middle of the semester, so you might be burdened by a lot of things from all the other courses that you have. Yeah, I had a good one, actually a productive one. Was able to finish a draft of my dissertation, but yeah, I hope you still found some time to relax because I did. I literally just watched Netflix for 2 days, slept, and just ate. So, all right. So now let's go back to business. I know that in the lecture, if I'm not mistaken, you did a review, an in-class review for test number 3. So actually, I'm not sure what to do right now. I didn't prepare any worksheet. So I am counting on you guys if you have some questions, some leftover ideas over the problems that you hopefully started working on during the spring break. So let me know. Yeah, Herson, it will be great if you can send me your questions. Yeah, sure. Actually, anybody, please send your questions if you have some things. Is it correct you did just a review for test number 3 in the lecture? Okay, great. And then you haven't started chapter 9 yet. Um, I don't have a copy of the practice test with me right now. I think that's different from this one. Review for test 3. I just downloaded it from your class notes. But if you have specific questions, kindly send a screenshot of them on the chat so I can take a look at them easily. And then I'll try to address them in the same order that I got them. Okay, great. I'm seeing a lot of questions here. Maybe that will be enough for the hour. Though I have a couple of problems here prepared for partial fraction decomposition still. But let me go over your questions. Let me make okay a note here. Let's call it a review for test 3. Let me see. Okay, the first question I got is to calculate this integral. So problem 1, um, integrate 4x minus 16 over x cubed plus x squared dx. All right. So if we look at this problem, well, we can try first because I guess in the exam or in this practice test or in your homeworks, you will not be told exactly what method to use in a particular problem. So it's up to you to decide what to do, right? What is the most appropriate technique to use? So I advise you to first try to see, at least in your head, if U substitution will work. That's the easiest, and you don't want to burden yourself with the other advanced integration techniques. So in this case, usually our target for the U substitution is to let U to be the denominator. But if you look at the denominator, it's x cubed plus x squared. It will require a du, which is equal to 3x squared plus 2x, which obviously cannot be found from the numerator. So that signals, okay, U substitution will not work. And if we look at the form of the integrand, it is a ratio between two polynomials, right? So chances are partial fraction decomposition will work for this particular problem, right? And remember, for partial fraction decomposition, the first thing to do is to check whether the denominator has a larger degree than the numerator, right? And in that case, yes, we have that case because the denominator has degree 3, the numerator has degree 2. So we can do partial fraction decomposition and say, okay, the next step would be to factor everything in the denominator, factor it completely. I guess the only thing we can do here is to factor out an x squared. So we'll be left with x plus 1 dx. All right. And then we do a partial fraction decomposition. And remember that the decomposition will depend on how the denominators look like, right? So in this particular case, we have x squared plus, times x plus 1. So first we have a quadratic factor x squared here. So that quadratic factor, non-repeated, we'll have one partial fraction for it. And then the numerator, remember the general rule for simple non-repeated factors, the numerator should be 1 degree less than the denominator. So the denominator here is degree 2. So the numerator should be 1 degree less. So it should be a generic linear function. So that means we have ax plus b here. For some constants, ax and b, that we will defer the computation of later, right? And then plus the other factor is x plus 1. It's simple as well, so it only gets one partial fraction. And then the numerator will be 1 degree less. This is degree 1, so the numerator should be degree 0 or a generic constant. I'll use the letter D here because I'm reserving capital C for the what do you call this? For the arbitrary constant that goes with integration, right? And then times dx. Let me just check the chat. Okay, yeah, Herson, that's right. You can also factor out the constant factor in the numerator, take it out of the integral, and yeah, that will give you the same answer. So, okay, but I don't want to worry about that right now, but you can do that certainly. So here I can, well, since this is a multiple choice problem, so you really need to compute all the constant factors, all the unknown constants. So what we'll do here is solve for A, B, and D first. But you can go on and do the integration right away because I think that's easy. But since it's a multiple choice problem, I still need to compute the constants. So I'll go ahead and do that. So we wanted 4x minus 16 over x squared times x plus 1 to be equal to ax plus b all over x squared plus d over x plus 1, right? If I do the multiplication, I'll multiply both sides by the denominator x squared times x plus 1. What we'll get is 4x minus 16 equals ax plus b times x plus 1 plus dx squared for all x's, right? Now, to find a, b, and d, we can take advantage of the fact that this equation is true for any x. So you can give any value of x that you want, pick the ones that are convenient to evaluate, or those will be helpful that will make one of the factors vanish. So in particular, if I will take x to be equal to -1, you see that this factor will be 0, effectively getting rid of the term with a and b, leaving us only with the term with d. So from there, we can solve for the exact value of d, right? So what I'm trying to say is if I plug in -1 on the left side, so you still need to plug -1 in here. Doing so will give you -4 minus 16, so that's going to be -20, equals the first term here will be 0 because x plus 1 will be 0. So we'll have just d. So d is equal to -20, right? And we can also let x to be equal to 0. In this case, we have -16 on the left. And on the right, we'll have, plug in 0, we'll get ax plus b. Oh, sorry, we'll get x is 0, so the first term will be gone. Hence, to get b equals -16, okay? Unfortunately, now we ran out of good x's that will make one of the terms vanish. So you can just give any arbitrary value of x you want and then use the previous values that we already know. So for instance, here I can let x be equal to 1, plug 1 into both sides of the equation. So we get 4 minus 16, so that's -12, equals, plug in 1, so I'll have a plus b times 2 plus d, all right? Then plug in the known values. We already know what b and d are, so I'll use their computed values here. So I'll have a minus 16 times 2 minus 20, okay? And then I'll solve for a. So this is a simple algebraic equation. Add 20 to both sides, so I'll get 8 equals a minus 16 times 2 Divide both sides by 2, we'll get 4 equals a minus 16. So that means a is equal to 20. Okay. So the original integral that we have, let me just put that here, is equal to, in the decomposed form. So let me copy this. Okay. But now we already know the unknown constants. So we have 20 there. B is minus 16. And then D is minus 20. Okay. And then I can further rewrite this as what I'll do is to perform the division here, because the denominator is a monomial, so it can go into the denominator of the first term and then the denominator of the second term. So we'll have 20 over x minus 16 over x squared minus 20 over x plus 1 dx. And then you can integrate them one by one. So you'll have 20 ln of the absolute value of x minus 16 x to the minus 1 all over minus 1 minus 20 ln of the absolute value of x plus 1 plus the arbitrary constant c. And then now, if you look at the choices, and this is the tricky part whenever doing a multiple choice type of question, you need to write exactly your answer exactly in one of the forms of the given choices. This might be tricky because you can, for a particular integral, there might be several ways on how to solve it. And the answers that you'll get might not be exactly written the same way. Actually, they could be completely different and just differ by a constant, and that will be that's a nightmare because you have to redo your solution, try the other technique that will give you one of the choices in the problem. But I guess here the only thing you need to do is to play around with the representation of the problem. I mean, so look at this term here and this term here. You can factor out 20 from that group. So you'll have 20 times ln of the absolute value of x minus ln of the absolute value of x plus 1, right? So what I did there is to group the first and the third terms together, factor out 20. So I'll have that. And then the second term can be simplified to plus 16 over x plus c. But this is still not one of the choices. So look at this and notice that you can apply loss of logarithms here. Whenever you have the difference of two logarithms with the same base, then you can write them as a single logarithm. So applying loss of log, you'll get 20 ln of the absolute value of x over x plus 1 plus 16 over x plus the arbitrary constant c. All right, and that's it. I see, Herson, you got the right answer. So let me see. Oh, unfortunately, this is not one of the choices still, but it is. It looks similar to letter E, which is the correct answer. And for that, we need to play with the loss of logarithms even more. So you can write this as x plus 1 over x raised to the negative 1. Because remember what the power negative 1 does, it will just flip over the fraction that you have. So here, x over x plus 1 can be written as x plus 1 over x raised to the negative 1. And then loss of exponents, this can come down in front of the coefficient. It's going to be negative 20 ln of x plus 1 over x plus 16 over x plus c, which finally is one among the choices. Well, I guess if you, I can't think of a shorter way than what we did here, but I hope that would be, this is fine. Did you do the same solution as I did? But of course, I think you factored out the constant or the constant multiplier from the top. I don't know if there's an easier way, but I guess this is not a bad one. Just a long one, but still manageable one. Okay, yeah, that's also fine, Herson, because one way that you can look at x squared, let's go back to x squared here, because here I treated x squared as a non-repeated quadratic factor, and hence I had ax plus b. But you're right, you can consider ax to be a repeated linear factor, x, right? X repeated twice. So you have a over x plus b over x squared. But actually, that's also what happened here. So I have a over x, b over x squared. They are equivalent. So yeah. Okay. Yeah, if that's fine, then I see you have. Yes, that's right, Herson. If your denominator is an irreducible quadratic factor, and when I say irreducible, it means it cannot be factored anymore. So the numerator should be a generic linear function, right? So that's why you see here, I treated x squared as a non-repeated quadratic factor, and hence the numerator is a generic linear function. So that's the general rule. If you have a degree n in the denominator, then the numerator will be a generic degree n minus 1. Okay, but your solution of writing the decomposition as a over x plus b over x squared is correct. That's also correct because you're looking at it as x being repeated twice as a linear factor. So they are equivalent, nothing's wrong with that. But I wanted to stick with the general rule that if you have an irreducible quadratic, the numerator is a generic linear function. All right. Okay, if that's fine. Herson, I see that you asked another question. Is it okay if I skip that one and go to Michael's question first? Okay, then I'll go back to your question if we have time. Okay, Michael, you sent this question. Oh, this is about Simpsons Rule. To tell you honestly, I already forgot the formulas here, so I need to pick to take a pick at the lecture notes, right? But essentially, you're asking about what is to estimate the error. For the Simpsons rule, with n equals 6, used to approximate the integral from 0 to 3 of sine 2x dx. Okay. Yeah, I need to take a peek in the textbook because I already forgot these formulas. Because usually we use computers to evaluate the numerical integrals for us. So we are not really, in practice, we are not memorizing these formulas, but unfortunately for you guys, you need to memorize it at least for the exam, right? Okay, so according to the textbook, this is the formula for the error for Simpsons rule. So the theoretical error, because there are several sources of error whenever doing computations via computer. Number one, you have the inherent or the intrinsic error, which we call the theoretical error from the method itself. Because remember, trapezoidal rule, Simpsons rule, left endpoint rule, midpoint rule, right endpoint rule, and all of these numerical integration techniques do not give us the exact value for the integral. They just give an approximation. So in the way that these methods were modeled, there is already an inherent or intrinsic error involved. So that's the theoretical error. Another thing that in practice we are concerned about is the computer error or the propagated error from machine calculations, because machines cannot, like computers, cannot perform many operations exactly. For instance, if you're dealing with sign values. So usually sign values are consists of infinitely many decimal places, right? But computers being finite machines, they can only handle, say, up to the 32nd decimal place. So there will be some errors that might pile up if you're doing complicated stuff, right? But we are only interested with the theoretical error, and the textbook says that the theoretical error for the Simpsons rule is this. So the error is at most b minus a raised to the fifth all over 180 n to the fourth times m, where m is what? Where m satisfies this inequality. The fourth derivative of f evaluated at x is less than or equal to m for all x in AB. Okay. So this is the statement of the theoretical error. Okay. So let's see what are the different parts in here. So it says that the theoretical error is bounded by b minus a to the fifth. So b is B is the upper limit of the integral. A is the lower limit, and then n is the number of points used, and then m is a bound, is a positive number that bounds the values of the fourth derivative of your function, right? So perhaps here the hardest part is to solve for m, because we already know what a is. So this is a, this is b, this is a, n is 6. So all of them are given in the problem. So the only difficult part here is the value for m. Now m is a bound for the fourth derivative, so we need to compute the fourth derivative. So if you look at your function, f of x is equal to sine 2x, your integrand, all right? The first derivative is what? The first derivative is 2 cosine 2x. Second derivative is negative 4 sine 2x. Don't forget that we are applying the chain rule here. Third derivative is negative 8 cosine 2x. And finally, the fourth derivative is 16 sine 2x, right? And then we take the absolute value. Oops, let me do it here. The absolute value of the fourth derivative of x is 16, absolute value of sine 2x, all right? And we need to find a bound for it, right? So, and that bound, right, remember, we need an m. M actually is the bound that we're looking for here. So we're looking for the value of m. And we need to find a bound that will hold for all x's between 0 and 3. Okay. Now, 16 is a constant, so you leave it there. If you look at the sine value, okay, now what would be the maximum value of sine 2x when x is between 0 and 3? Well, an easy choice will be to say that sine 2x is maximum when the sine is equal to 1, right? Because if you go to the unit circle, the maximum value of sine is equal to 1. It never exceeds 1, right? So you say that, okay, this value is always less than or equal to 16 times 1. Yeah, you're correct, Muriel. Yeah, you can take this 16 to be your value for m. Okay, because when the sine is equal to 1, because our usual choice whenever you see trig functions like sine and if you see trig functions, sine and cosine, we know that the values are always bounded by 1. Okay, so it's always bounded by 1. So it doesn't matter, you can always choose 1. But if you want to have a tighter bound, you need to make sure that the 1 is attained over the interval. So we are on the interval 0, 3, but sine takes the value 1 at pi over 2. Right? So that means pi over 2 is about what? 3.14 over 2, so 1.5 something. So definitely, that will the sine function will attain the value 1 over this interval, right? because 2x will be between 0 and 6, so pi over 2 is definitely inside that interval. So now you can say that the error is at most b minus a, which is 3, all over n, which is 6 to the 4th, times 180. So let me see the formula again. B minus a to the 5th over 180 times 6 to the 4th times 16. And that would be your bound for the error. I guess in your choices, everything is expressed in terms of decimals, so you need a calculator to evaluate this. I don't think you are expected to do this by hand. So if this would be the free response part of the exam, then your answer could be left at this form. All right. Yeah, that's correct, Michael. If it's the Simpsons rule, m is computed by looking at the bound for the 4th derivative. For the trapezoidal rule, it would be using the 2nd derivative. And that's why theoretically, you see, the more points you use, the better the approximation will become, right? I guess you have seen a picture about it in the lecture. You see that if you're looking at the area of the curve, and then you subdivide it using a finite number of subdivisions, so you have a finite number of trapezoids. Intuitively, or looking at the picture, the more trapezoids you use, the better the approximation becomes, right? And that is actually back up by our by the theoretical error formula, because you see that b minus a to the 5th is a constant, right? Because that's just the length of the interval raised to the 5th. M is a bound on the 4th derivative, that remains the same. But if you use more points, that means n is larger. What happens to n to the 4th? N to the 4th becomes larger, right? And when the denominator becomes larger, the entire quotient or the entire expression here becomes smaller and smaller, right? So theoretically, the more points you use, the better the approximation is. So if you want a very good approximation for the integral, theoretically, you can say take n equals 1000. That will give you a very good approximation, at least from the theoretical point of view. But that will not always happen, because you're doing the calculations in a computer. The more operations you ask the computer to do, the truncation error, meaning the decimal digits that were ignored by the computer whenever doing the calculations in it, because it is a finite machine, it can handle only, say, the first 16 decimal places, and when you do 1,000 calculations there, those truncated decimal digits might cause you some trouble. So there's always a give and take. And of course, the more points you use, the more operations should be performed, so the calculations would be much more expensive. Okay. So, okay, I hope that helped. Let me see who's the next question is. Okay, so I just see questions from Herson and Michael. How about the others? Do you have questions? Because otherwise, I'm gonna go over their second questions. Okay. While waiting for the others, if they have questions, Herson, were you able to answer your second question with the x squared minus 11 in the denominator? Because if you want, we can still talk about that for the benefit of the others. Okay, yeah, let me see. Okay, maybe I'll do that quickly for the benefit of the others, and then go to Michael's next question. Okay, so problem 3. Okay, let's have this. So you have the integral of 3x squared plus 33 all over x times x squared minus 11 dx. Use substitution. Let's see if that will work. Actually, it won't work because the denominator, let's see. Yeah, if you let u to be the denominator, you will need a du equals 3x squared minus 11, which you cannot see from the numerator. You can manipulate the numerator, but it would be messy. So I guess here we can do partial fraction decomposition. And then if you look at the denominator, it is not factorable with in terms of the polynomials with integer coefficients. So you can treat it as an irreducible linear factor. Uh, but actually, the choices seems to allow factoring it as x minus root 11 times x plus root 11. But you can do that. But of course, nobody likes to work with square roots. So maybe I'll split it up as this. Okay. First factor is x, which is linear. So it will get one partial fraction with a generic constant on top, plus I'll treat x squared minus 11 as an irreducible quadratic factor. So it is simple. I mean, it's not repeated. So it gets one partial fraction. Since it's quadratic, its numerator should be a generic constant. Sorry, a generic linear function. Okay. Then we have this. And then we need to solve for a, b, and d. So on the side, we want 3x squared plus 33 over x times x squared minus 11 equals a over x plus bx plus d over x squared minus 11. Okay. And then we want, we do the cross multiplication. So this gives us 3x squared plus 33 equals 8 times x squared minus 11 plus x times bx plus d. All right. Then you can, this is true for any x. So you can pick your favorite x's. So if x is equal to 0, I guess that's the easiest choice. If x is 0, we get 33 equals negative 11a. All right. So this implies that a is equal to negative 3. Okay. But again, of course, you could have factored 3 out of the numerator. That's fine. Another choice would be what? Well, you can pick x equals 1. Actually, I'm thinking of choosing x to be equal to root 11. That's also fine. Well, maybe let's try that. Okay, if x is equal to root of 11. If x is root 11, so we'll get 3 times 11 plus 33 equals, the first term will vanish, right? Because I'll have here root of 11 squared. That's going to be 11 minus 11, so that's 0. Entire first term vanishes. So the next term would be root 11 times b root 11 plus d, okay? Or this would be 66 equals 11b plus root of 11d. All right. Unfortunately, here I have two variables, b and d, or two unknowns, b and d, with only one equation, so I cannot solve it at this particular form. So I need another equation, and I can get that by choosing another value for x. Say I'll choose root of negative 11. Of course, you can choose any other x value that you want, okay? But I guess I'll stick with this one. So if I plug in negative root 11 to both sides of this equation, I'm gonna get what? I'll get 66 still on the left side. And then I'll still get a 0 in the first term, right? Because negative 11 to the second power is also 11, okay? Then on the second term on the right, I'm going to have negative root 11 times b times negative root 11 plus d, okay? I simplify my right side now, it's going to be, okay, 11b minus root 11 times d. Okay, let's call this equation 1. Let's call this equation 2, right? So let's just put them side by side. Duplicate. Oops. Right? And then this one. Let's put them here. So we now have a system of two equations, right? So involving B and D, and you can use your favorite technique from algebra on how to solve this type of equations. I will do elimination. Hopefully you still remember that. That will be helpful here, because here I can add the two equations together, and if I add them, you see that the ones with the d's will cancel each other out, right? So we'll have 2 times 66 equals 22b. I just don't want to do the division, so I did that. And then we find b to be equal to 2 times 66 over 22, right? But note that 66 over 22 is just 3. So that means b is equal to 6. Okay, now we get the three values now, the two values a and b. Now let's look for d. For d, you can use either equation 1 or 2. Let's try equation 2. Using equation 2, we'll have 66 equals 11 times 6 minus root 11 times d. Okay, this would be 66 equals 66 minus root 11 times d. That means 0 equals negative root 11d. And Herson is correct. D is equal to 0. So, okay, yeah, double check your answer, Muriel. It appears that D is equal to 0. Yeah. Okay, so now let's go back to where we started. Okay, this is what we're looking for. And you see how tedious the algebraic step is compared to the actual calculus step here. So here we knew that a is equal to what? A was -3, right? So it's -3. And then d is 0. That's good for us. B is 6. So we'll get 6. What's that again? So we'll get 6x here. Okay. Okay, so now we can integrate this, I think. For the second term here, I guess we need a u sub. So here we need to let u to be equal to x squared minus 11. Du is 2x dx, or 6x dx is equal to multiply 3 to both sides, so we'll get 3 du, right? So essentially we'll have integral of -3 over x, and then we'll have 3 du. Maybe it's not good to write it that way. I'll evaluate the first integral first. So I'll have -3. It's going to be -3 ln of the absolute value of x plus the integral of 3 du over u. Yes. And finally, we'll have -3 ln of absolute value of x plus 3 ln of the absolute value of u plus an arbitrary constant c. Then we'll go back to x. All right. And then I don't know if this is part of the choices. Let's see. Oh, luckily it is. So we're done. So this is your answer here. Okay. So the lesson about this problem is you need to remember how to solve systems of linear equations, at least the basic ones, because there would be times that you will be running out of choices for x that will make or that will reduce the number of variables to just one. insofar as this equation is concerned. So you really need to deal with systems of equations like this. All right. So hopefully that makes sense. Let me go to Michael's second question. And this would be problem 4. Michael's other question is about finding the arc length of f of x equals x squared over 2 from x equals 0 to x equals root 3. This is about finding the arc length. So this is chapter 7. But I'm not sure if that is still covered in test number 3, unless this will require you some techniques from chapter 8. I'm not sure where Michael got this. So if you're still there, Michael, you can. Oh, it's in the practice test. So maybe you will need some techniques from chapter 8 to solve this one. Because let's see. So recall that the formula for finding the arc length, let's call it L, is the integral from a to b of the square root of 1 plus the derivative squared dx. So the first thing to do here is to find f prime, then square it. Okay. So note that f prime of x, so the derivative will just be x. All right. Then f prime of x quantity squared will just be x squared. So we put that into the formula. So the arc length would be from integral from a to b. So that's going to be 0 to root 3. Okay. Is the upper bound really root 3? Yes, it is. So, then we take the integral of 1 plus x squared dx. Okay. Oh, that's why I see that this is still in the practice test, because you need trig sub, right? And that's why, yeah, because here we cannot get rid of the square of the radicals, because when we did arc lengths back in chapter 7, we relied on the square root to be gone naturally, because from the problems we had in that section, the radicand is a perfect square, right? So that's why the square roots were gone. But in this particular example, it is not gone, because this is not a perfect square. We cannot get rid of the square root alone. And Herson is correct. We need trigonometric substitution here. And if you recall, we need to let we need to let x be equal to tangent theta, right? Because here, this we need to use the Pythagorean identity that involves tangents and secants, right? So for that, we'll need a dx equal to secant squared theta, d theta, right? So for now, I'm going to work with an indefinite integral first, so that I don't need to change the bounds. Because as you have seen in the last exam, we had been a little bit strict with the notation. So if somewhere in your solution you changed the variables, but you didn't change the bounds, some points were taken off. So if you don't want to worry about changing the bounds every time you change the variables, you can solve the indefinite integral first, and then just use the fundamental theorem later when you have everything back into the original equation, in the original variable. Okay. So here, I just ignore the bounds, at least for now. And then I'll perform the trigonometric substitution. I'll replace x by tangent theta. So we'll have tangent squared theta over there. And then dx will be replaced by secant squared theta, d theta. Okay. Then I'm going to use the Pythagorean identity that tells us 1 plus tangent squared is secant squared theta. And we have a secant squared theta outside. And this is actually the reason why we're doing trig sub, because trigonometric substitution can turn the radicand that is not a perfect square into a perfect square. And being a perfect square, we can get rid of the radical, because the radical was really the pain in this problem. So square root of secant squared, assuming secant is in the right quadrant, or I mean theta is in the right quadrant, we can write it as secant theta times secant squared theta d theta. And then here we'll have secant cubed theta. Now I'm trying to recall what's the right technique to do this. At this point, you only have two choices, right? Two choices. First, you can write secant squared in terms of the tangent, right? So if you write it in terms of the tangent, yeah, I guess we can do that. So, because actually that's my only choice here. So I'll have secant theta. Then secant squared is back to 1 plus tangent squared theta. D theta. Oh, is that right, Michael? If you were told to memorize secant cube, then you don't have to go through this long solution that I'm about to do, because this will involve either integration by parts or breaking this down into several pieces. Because I will need to write it as a secant right away. So, okay, if you were told to memorize secant cube, then I'm gonna follow that. Okay. And unfortunately, I am not good at memorizing. I hate memorization. That's why I'm ready to evaluate this manually. So let me just compute, take a peek and look at what's the integral of secant cube. Secant cube. Yeah, you need integration by parts for this, and you will have 1/2 secant x tangent x plus 1/2 ln of secant x plus tangent x plus the arbitrary constant c. Yeah, they both have 1/2. Yeah, if I'm taking Cal 2 right now, I wouldn't memorize this formula for secant cubed, and I will just do integration by parts. But that's just me who hates memorization. Okay, so that's it. Oh, actually, my variables here are wrong. The variables are theta, or are thetas. So here. Oh, this is yeah. Thank you, Michael. And then we need to revert to the original variable x. Remember here we let recall we let x to be equal to tangent theta, if I'm not mistaken. Yeah. So that means x can be thought of as x over 1 and tangent from SOHCAHTOA as opposite over adjacent. So that means, all right, if theta is here and the right angle is over here, that means opposite theta, x should be here, 1 should be here, and the hypotenuse is 1 plus x squared. So the integral from root 0 to 3 of square root of 1 plus x squared, which is actually our arc length, is equal to, okay, 1/2 secant theta. What is secant theta? That's the reciprocal of cosine. So that would be hypotenuse root of 1 plus x squared over adjacent. So that's going to be over 1 times tangent theta. Tangent theta is just x plus 1/2 ln of secant theta. So that's root of 1 plus x squared plus x evaluated from 0 to root 3. Okay, just do here. Okay, and so we plug in root 3. So we'll have, let's see, so I'll have 1/2 times root 3 times, if you plug in root 3 here, so I'll get 3 plus 1, that's 4. Root of 4 is 2. So, okay, I think that's it for the first term. Plus 1/2 ln of 2 plus root 3, okay? Minus, if we plug in 0, first term vanishes, second term will be 1/2 ln of 0, 0, ln of 1, which is also 0. So this guy is also 0. So our answer is root 3 plus 1/2 ln of 2 plus root 3. Barring any silly arithmetic mistake. Okay, is that good? Let me see. Okay, so any other? Oh, it's already time. So any questions with this problem that we just solved? So I guess if this is in the practice test, so this is sort of a hint that, or a reminder that you cannot just forget all of the things that we discussed in previous chapters, because they might pop up in the exam, right? Just as like this one. So yeah, at first I was a bit skeptic that this is in the practice test, but I know that there's a chance that it is, because usually computing arc lengths requires integrating a square root. And actually, that's what happened here. So this is sort of a hybrid question consisting of techniques from chapter 7 and 8. And it's not just that, because here we did trig sub, but inside trig sub, we needed to do powers of trig functions for the secant cubed. And if you didn't memorize secant cube, then you need integration by parts. So this is a very profound problem, right? Okay, so I guess that's it for today. What do you want to do on Tuesday? Oh, sorry, on Wednesday. Will you be? Do you know if you will start something, or will you start with chapter 9 on Wednesday in the lecture? Because we can still do a review for for test 3 if you want, but please send me questions so that we have something to discuss. Otherwise, I'm gonna go over. Oh, you already finished the class review? Yeah, sure, Muriel, that will be great. So yeah, we can go over some of your written homework problems. It is due on Thursday, if is that correct? Or is it due tomorrow? I'm not sure. Let me just do a quick check. Oh, it's due on Thursday. So yeah, so that will be great. We can talk about your questions about the written homework on Wednesday. Plus, if you still have some problems for the test, and then if nobody's asking questions, probably I'll start with some problems from chapter 9. All right. I think that's a good plan. So that's it for now, guys. So thank you for coming today. And oh, that is a cute meme. Just made my day. Okay, so that's it for today. See you on Wednesday. All right, bye, guys.